Good afternoon, everyone. I'm Gonen, a research intern in Korea Institute of Science and Technology, and today I'm here to present you my work, which is Imitation of Human Upper Body Motions by Humanoid Robots. First of all, imitation is the action of using someone or something as a model. It's as simple as copy and paste. You just need two things, which are a model and a copycat. In our work, the model is a human's upper body motions, and our copycat is now robot version 5 by Aldebaran Robotics. To track human motion, we use two different sensors. One is markerless motion, Microsoft Kinect, and the other is marker-based motion analysis motion capture system. After tracking data with sensors, we made all calculations using Python programming language and controlled the robot using ROS Indigo and NoQ API. Now let me explain the whole process. For a successful imitation, a well-defined robot model is needed. And we create now's model using modified DH parameters. It gives us 4x4 matrices, which includes both position and orientation information for each frame. And a frame can be defined as a joint or an end effector or a special location on the robot. There are 23 end effectors and one torso point that is center of now. And they contain information with respect to their antecedents. By multiplying them in a hierarchical order creates dynamic geometric model of an end effector, and this multiplication transforms them with respect to initial frame. Also, symbolic derivatives of give a direct geometric model gives us the direct kinematic model of the robot, which is Jacobian matrices. And in my solution, I use these Jacobians. I just save them as a separate file, and when I need them, I'll just call back. So far, we have a robot model, and now we need a human model for imitation. In this project, as I mentioned before, we have two different sensors, and the main difference between them is in motion capture. We have just human skeleton, I mean the positions of these points, and in motion capture system, we have both position and orientation information. So I have a robot model and a human model. Now I can do the imitation. In this, I'll propose an algorithm in a flowchart. Now here let me explain it. First, we take data from sensors and process it. Second, we transform coordinates. Then we scaled human size down to robot size, considering both direction and their lengths. After that, we calculate joint angles. In Kinect, we use trigonometry, but in motion capture, we use orientation information of the sensor and save these angles to be used as reference angles in inverse kinematic solution to a CSV file. In the sixth step, we create vectors of current and desired end effector positions for both joints and for end effectors. And then I have three tasks in one iteration steps, which are end effector tracking, joint limits avoidance, and joint trajectory tracking using which are using reference angles I previously calculated. And I have different change of angles from each task. And after summing them up, I have solution after one iteration step. Then I check constraints. If they are all okay, I'll go next frame. If they are not okay, I'll do this iteration one more time. Now here, there is a video presenting our work. First, I want to show you the Microsoft Kinect dataset. Here, blue skeleton is human that is stirring a cook. But USC data is too noisy, and I smooth it and scale it down to robot size, as you can see as red line. When we play the final result on the robot, you see the result. And second, I want to show you the motion capture system. I wear a special suit for it, and I put markers on my joints so that the 8 cameras can track my motion. And using Cortex software, I can calculate human skeleton, as you see. Then, similarly as in Kinect, I scaled my model down to robot size. Here I'm shaking my arms as if I am walking. Now you can see the result. And now I want to compare my solution. These graphs show the joint trajectory for model and for robot. Blue lines show the human joints, and orange lines indicate robot joints after inverse kinematics. As you can see, they are quite close if you consider the both joint limits of the robot. And I want to talk about the problems I encountered. The main problem is the difference between human and humanoid robot. For example, joint limits in human are wider than robots. Also, workspace of human is completely different than humanoid robot because the ratio between human limbs is different than robots. In addition to that, the humanoid robot has less number of degree of freedoms compared to human. Also, we encountered some problems while we are using sensors. Dealing with their calibration and noisy data makes our imitation solution complicated. Also, in motion capture systems, marker positions are quite important. We shouldn't hide markers while we are performing our gestures. If we go over to my contributions, I suggest a solution which deals with both direct and inverse kinematics. And it is compatible with any sensor and a robot type, and it can be extended to another lower body, which we did, but unfortunately this part is not on our paper. Here I add center of mass tracking and lower body left foot as an end effector, and I am just bending my knees. And we got our first results a couple of weeks ago, so it can be considered as it is in progress. And I thank you all for your attention. If you have any questions, you can ask me. Thank you.
Thank you for the presentation. We are already buying the time. We could allow